Okay, now on to this part. Now, this part, it might be a little bit hard. I'm going to go a little bit faster, so if you need some time to refresh with the previous videos, that's completely fine. You know, these are videos, these are not lectures, so you can always press pause and just take some time, or you could just stop, right? Just go back and then, you know, absorb a little bit more of the knowledge from the previous videos and then just come back to this. Okay, so for when you differentiate the inverse functions, you will have to learn this. You have to remember these three equations, and you will also need to learn implicit differentiation. All 6 of these have the same method of solving, so I'm just going to start with arcsine. Right. So if you remember, right, f, a function and an inverse function, they cancel, right? So since we don't know how to differentiate this, but we know how to differentiate sine, I will just take sine on both sides. And this will become x. I differentiate both sides. This will become cosine y dy dx. This will become 1. And then I isolate dy dx. It will become 1 over cosine y. Now technically this is the tangent, right? This is the slope, the dy dx. But here I use the variable x. Here I use the variable y, right? I don't know who y is, right? It's not my brother. I don't know who he is, right? I know x is my best friend. So I have to turn this back some way. Now, when you look at these 3 equations, you realize that cosine here and cosine here, they look pretty similar, right? It's just that the square here is a little bit of a problem. So what I would do is just take a square here and then I just root this. You know, I did nothing, right? I square it and then I take the square root, so I just end up with the same thing. But what you can see here is that if I use the equation now, I take sine and I put it back, and something very magical will happen. What is this? 1 minus sine square y. Okay? If I erase this for a little bit, you realize that sine y here is equals to x, right? I'll just put these back. So I could just turn this back into x now. It's 1 minus x squared. And that's your answer. It's 1 over square root 1 minus x squared. That's basically how you do all of them. Okay, so I'm just gonna skip to the tangent one and then just go back to the ones with a c in it, because you realize that they have a very good pattern. So same thing, another color. Same thing, y equals tangent, arctangent of x. I take tangent on both sides. I differentiate this side, differentiate this side. This will be equals to 1. This will be equals to secant square secant square y dy dx. I isolate dy dx. I'll get 1 over secant square y. If I have to turn y back into x, I will use this equation up here. And this is perfect, right? You don't even have to change. You don't have to do like algebra and finicky and stuff. So it's just 1 plus tangent square y. So tangent y is equals to x from here, right? So this is just 1 over 1 plus x squared. Okay, next one, arcsecant is y Same thing, take secant on both sides. It's just x. I differentiate both sides, right? This I would get secant y tangent y dy dx. And then here I would get 1. Yep. And then dy dx, I will isolate this. This will become 1. And secant y tangent y. And you realize that for this one, secant y is equals to x, and I have secant y here. So I can just take x out already. For the tangent, it would be, I would use this equation right here, and then the same way I did with the sine, I would just take a square and then I will root this. So tangent square y would be equals to secant square y minus 1. And secant square y minus 1. And then since secant y is equals to x, this will be equals to x squared minus 1. Okay. Now, one thing that you have to remember for this one is that this has an absolute value. And the reason why, well, it's hard to prove this algebraically, so we just look at the graph for here, okay? So this is a graph of arcsecant, and then you realize that all of the slopes or all of the tangents on this graph, they are positive, okay? The most, when it's approaching negative infinity or positive infinity, they will approach 0 somewhat, but they will never become negative, right? And that is why you have to put an absolute value on the x to make sure that it will never become negative. And the reason why you don't have to do anything for this is because anything that comes out as square root is positive, and that is why. So here it will just be 1 over absolute value of x, and then x squared minus 1. Yep. Okay, for the rest of these, you do them the exact same way, right? I'll just do the cosine one. Y equals arc cosine x. Cosine both sides, differentiate both sides. This will turn out to be negative sine y dy dx. This will become 1. Okay? You isolate dy dx, this will be negative 1 over sine y. You square and then you root, and then look back at the top. This is similar to this. This I put this back. It'll look something like this. And then cosine y is just x, so I can just do this minus x squared. Yep. And I'll just write this back at the top. Now, what you'll realize is that these are very similar. It's just that there's a negative here, right? So the same way you do the differentiation, if you see a c, then it is a negative. It is the exact same thing for the rest of these. This is negative 1 over 1 plus x squared. And then this is negative 1, absolute value of x, root x squared minus 1. Okay? You can continue to prove arccotangent x or arccosecant x, but I already did 4 of them you should be able to do the rest of them, I think. All right, and then just two more. I'll give it a little preview. It's just two more, and then the second principle, and we'll be done with this chapter.